Yeah, here we go. Okay, good. The beginning of video 37. This is actually it's been a while since I put up a video because I just got back from Mexico. So I'm just putting up video 37. You're only going to have two more videos, video 37 and 38. Yeah, the next topic is logistic regression, as you can tell, and this is some of my favorite stuff. And I was so tempted to go completely crazy with it and get into some what I think is really cool stuff. But we'll save it for the next stats class that hopefully you guys will take from me. So what I want to do with logistic regression is just get into the very basics. So video 37, we're going to look at logistic regression from a simple linear regression perspective. Although, everything that we've learned with simple linear regression and multiple regression certainly kind of apply, but there's more differences than there are similarities. Video 38, what I want to do is get into multiple logistic regression, how we handle this scenario when we want to use multiple predictors, which is obviously usually the case. So what I'm going to do here, I'm going to start out with a very simple example. First of all, get into a little bit of motivation for logistic regression and some of the ins and outs of the procedure. And then we're going to look at a very simple example, and then I'm going to move into R and show you how we conduct these using the statistical software package. So guys, I'm going to probably take a little bit of different approach here. I'm going to type out some things. I want to be able to go back to the blackboard when I get into notation and graphs, but some of the things that I think are super duper important. Let me go ahead and get my bullets started here. I'm just going to type it out instead of. I think this will probably work the best. So anyway, what I would want you first and foremost to know about logistic regression is it's very similar to what I would call simple linear regression, but also very different. Logistic regression is different because our dependent variable is dichotomous, and we usually think of dichotomous variable as being coded zeros and ones. So the motivation here would be, if you can imagine, or at least I hope you can imagine, lots of different types of research goals that may have a dichotomous dependent variable. For example, well, I don't know, in our previous presidential election, maybe we wanted to know what characteristics differentiated between those who voted and didn't vote. So our dichotomous there would be vote versus did not vote. Maybe from the educational perspective, we would want to know why some people complete their degrees and some people don't. So again, we have a two situation where people complete their degree or they don't. From a health perspective, an emergency room may want to take initial data or initial information on someone coming into the emergency room and be able to use that to predict who lives or doesn't live. There's one I saw recently. It dealt with one of the hurricanes. Maybe I'm not going to say, but it was one of the recent hurricanes, and they did a logistic regression model looking at the characteristics of who evacuated versus who did not evacuate. Again, dichotomous. So logistic regression would be appropriate. And some of the predictors they used were whether or not the person had a pet. And believe it or not, people who had a pet were less likely to evacuate than those who did not have a pet. They also looked at people who lived in mobile homes versus not mobile homes, and it wouldn't be surprising that people who lived in mobile homes were more apt to, or more likely to evacuate than not to evacuate. So, guys, we can use categorical or quantitative predictors, but the dependent variable in the logistic regression case is always dichotomous. This or that, true or false, live or die, succeed, not succeed, evacuate or not evacuate. Now, let's go back to the air server and let me give you an indication of what happens with the logistic regression model. The goal here is to predict group membership. And I hope you understand what I mean by that. Group membership would be, either evacuate or not evacuate, live or die, fail or succeed, complete your degree, not complete your degree. Another way of thinking of this is we want to predict probability. And that's the ugliest R. Yes, Bailey, what's up? No, she has not. Would you give it to her, please? All right, sorry. All right, so to predict probability. Now, guys, in a standard simple linear regression case, we typically have an X value and a Y value where these are both quantitative, and we're going to get a situation where we may have a scatter plot that looks like that. Our goal is to predict a linear model using the least squares approach, which minimizes the sum of the errors squared. And we've been through that ad nauseum. Well, boys and girls, this is not what we do here. What we do in a logistic regression case is we have an X value, which again can be quantitative or categorical. The way I'm going to illustrate it here, it's going to be quantitative. But the Y value is probability. So guys, our Y axis is restricted to the bounds from 0 to 1 because obviously probability can only take on values between 0 and 1. So the kind of situation we get in here is we get into, if we have a logistic regression model, and that one's just about as ugly as I've ever drawn. But imagine having a set of data that looks like this. Now, obviously, guys, if we try to fit this with a simple linear regression model, we have major problems, first of all, with the distribution of the errors. But we also have a fundamental issue in that we have predicted probabilities which are above 1 and below below 0 and above positive 1. And again, we're restricted on the range of probability values between 0 and 1. What we want to be able to do, and I'll do this with yellow, is to come in and create what's called a logistic model that more appropriately fits the purpose of the study. Now, the technique here that we use instead of simple linear regression, where we use least squares, we use maximum likelihood estimation. And I have to admit, when I laid out the class many months ago, I was prepared to go through the process of MLE, show you some really cool features. It works similar to what we've done in the past. It's modeled by the Bernoulli distribution, with in the end a couple of nuances, and I'll talk about that in just a second. So maximum likelihood estimation is used to estimate the coefficients. All right. Yeah. The dilemma is this. Unlike with simple linear regression, there's no closed form. I don't know how I want to say this. There's no closed form for the optimal solution. So what we end up doing there is we either depend on computers to make to go through the iteration process, or we learn. I was going to again prepare to teach you the Newton Raphael, I forget exactly how you say that method, but that's going to have to wait until the next class. So we're going to take it easy here. Now, again, I don't feel like it's fair to throw a lot of stuff at you at the end of the semester. I always hated when professors did that. So we're going to kind of cruise on out and look at look at logistic regression in its simplest case. If I don't know really where I want to go from here. Ultimately, like with any maximum likelihood estimation procedure, what we're doing there is we've got a likelihood function L, which gives us the probability, or the likelihood of observing a particular set of values, our data. And, obviously the process is we look at the likelihood function, take the log of the likelihood function. And guys, at the end of the day, there's something called a -2 log likelihood value. That the iteration process seeks to minimize. Now, I'll point this out to you, when we get into R. It's not going to be something that we're going to crunch out theoretically or even crunch out by hand. But that's ultimately the goal of the maximum likelihood estimation process. You're going to learn a lot more about that in the next class. So guys, again, thinking about the computational method, multiple regression uses the least squares method to find the coefficients for the independent variables. And what we're trying to do there is we try to find where the sum of the residual squared is minimized. Logistic regression doesn't use that. It doesn't apply. We don't have a nice distribution of our errors. So logistic regression uses maximum likelihood estimation to compute the coefficients. Again, there's no closed form, so there's an iteration process. Again, that I'll show you as we go along. So gang, let's get into a little bit of what we need. Let's get down to the nuts and bolts of what's going on. First of all, we need a quick review on probability. Hold on. It's weird. If I can get dust on my pen, which I don't have here. All right, hold on, guys. This is annoying as hell. Surely to goodness I can find some dust. Okay, that may be the single strangest thing I've said yet. I got to find some dust in my house. All right, guys. Oh wow, that's much better. All right. Funny how you can always find dust around TVs. So, guys, probability versus odds. It's something you probably know, but again, I don't want to take the chance. So, let's say that we have a jar, and let's say that we have 5 red marbles in the jar, and we have 10 blue. marbles in the jar. So guys, obviously the probability of selecting a red marble would be 5 out of 15. Probability of selecting a blue would be 1 minus 5 out of 15, which would obviously be 10 out of 15. Now compare that to the odds of selecting a red. And the odds is just can be thought of as the probability over 1 minus the probability. This can also be seen as just taking the number of successes divided by the number of failures. So in this case, guys, we can simplify this and not look in terms of probability, but just look in terms of there are 5 red. So the odds of getting the number of ways to get a red are 5. The number of ways to not get a red are 10. So guys, obviously the odds of getting a red would be 0.5. Now, the odds of getting a blue, or let's just call that not red, would be 10 over 5, which is equal to 2. Now, I want to concentrate on this part right here because there's a very, very kind of simple thing that happens, but I don't think it's intuitively clear. Now, when we look at odds, the possibilities for odds run from 0 to infinity, and you may think of the center, which is clearly not the center, but kind of the balancing point of odds as being at 1. That's where the odds would be equally likely. For example, if I had a jar of marbles where I had 5 red and 5 blue, then the odds of getting a red would be 5 to 5, which would obviously be 1. Odds aren't centered. And in statistics, this creates an issue for us. So what we'd like to be able to do is we'd like to be able to center these things. Well, it turns out if we take the natural log of the odds, we do precisely that. So if I take the natural log of 5 over 10, I get negative 0.69. No, I don't. Yes, I do. And if I take the natural log of not getting a red, I get positive 0.693. So guys, by taking the natural log of the odds, what I do here is I actually center at 0, and I have a range from negative infinity to positive infinity. So long story short, if I take the natural log of the odds of something happening, the natural log of that event not happening can be thought of as being balanced around 0. So typically one will be, well, not typically, one will be 0. I'm sorry, one will be positive and one will be negative. Now, a lot of times when you talk about odds, you see odds in terms of probability. So we can think of the odds of some event as being the probability of the event over 1 minus the probability of the event. But always keep in mind that if the probability of some event E can be thought of as taking the successes divided by the total, like we did early on. We took 5 out of 15 because there's 15 total marbles, which would be our N, and there were 5 red. So if the event is getting a red, then this could be thought of as we have 5 red marbles out of a total of 15. Completely different than taking the odds, right? The odds, we would take 5 over 15 minus 5. Well, I'm sorry, and using the probability, we would take, this would be seen as 5 out of 15 over 1 minus 5 out of 15. So if we can think, therefore, of the probability of not having this event, then we would have 1 minus x over n. And guys, just a little bit of arithmetic here. We can see that as n minus x over n. So guys, the odds, therefore, of the event E, which can be seen as p over 1 minus p, could also be seen as x over n divided by n minus x over n, which is just x over n minus x. So guys, this up here gives us the odds in terms of the probability. This down here gives us the odds in terms of the count. This is typically the way that I'm going to put the odds. I'm going to count the number of successes and put on the denominator the number of failures. Okay? So just subtle. Hey guys, hey. Down just a little bit. All right. Let's get into a kind of a I don't know, kind of a cool example. There's an example I use a lot in a few of my undergraduate classes called the Titanic Example. And if you look at survival on the Titanic across females and males, and look at that across survive and not survive, well, it wasn't good to be a male. And it turns out that the survival, not survival rates for males and females were as follows. I think it's still kind of interesting to see that when we sum up the columns and the rows, that the total passengers on the Titanic were 1,313. So if you're a firm believer that 13 is an unlucky number, the Titanic was doomed from the beginning. So next time you go on a Carnival cruise, look at your registry, and if there's 1,313 people, I think I'd be bailing. Or drink a lot of tequila. All right, gang. So this is the way things work out, okay? Now, first thing I want to look at is I want to look at some odds. So I'm going to be going back and forth to this quite a bit. So what you may want to do when you're taking notes, you may want to pause a little bit and write this down, because we're going to take this 2x2 table. Well, I guess it's 3x3 now, but 2x2 table and do a lot of stuff with it. So first of all, let's get into what the purpose would be here. Now, we could ultimately have 4 different purposes. We could, use gender to predict not survive, predict gender to do survival, We could look at females surviving, females not surviving, males surviving, males not surviving. So what I'm going to do is I'm going to be more specific and go ahead and look at my goal. And what I want to examine in this case is I want to examine the odds of survival for males. So that is my goal. Now, because I've chosen survival instead of non-survival, I'm going to code survive as 1 and not survive as 0. Now, if I had chosen to examine the odds of a female not surviving, then I would have wanted to code not surviving as 1 and survival as 0. So whatever my focus is, let's say in this variable, which I've chosen survival, I want that to be coded as 1. Now I've chosen to examine the survival for males. So I'm going to code ultimately the males as 1 and I'll code females as 0. And obviously if I had chosen to look at the odds of survival for females, which would be an equivalent research statement. Well, in so many ways, I would have coded the females as 1 and males as 0. But this is what I want to take a look at. Okay, so from this, I would be interested in looking at the odds of let's see. I want to write this. Male survival to female survival. Well, if I look at the you know what, gang? I don't want to do that. I want I want to do something else before. I don't think it's going to be clear where I'm headed with that, unless I put an intermediate step in here. Okay. So, guys, let's go back to. I'm just going to go zeros and ones now since they've been defined, and I got 154, 308. 709 and 142. All right, now if I look at the odds of a female surviving, then I am going to have I have 308 females who survived, and I recorded 154 females who did not survive. So guys, I think if my mental math is correct, that gives me an odds for female survival of 2. Now I want to come in and I want to look at the odds of a male surviving. And you can see it doesn't work out well for males, okay? The odds of a male surviving, there were 142 males who survived out versus 709 who did not survive. And let me grab my calculator real quickly. And hey, girls, hold it down just a little bit, please. So 142 divided by 709 gives me 0.200. That's interesting. All right, so wow. All right. There was a delay there. So 0.200. So we can say that the the odds of a female surviving were 2 times more likely than not surviving. The odds of a male surviving were 0.2 of not surviving. A good way of thinking of this would be to think of the inverse. So 0.2, take the inverse of that, which is like 4.99. So you can think that the odds of a male not surviving, which again is just 709 divided by 142, were about 5 times higher than surviving. But guys, we have to be consistent because of the research, the way I set the goal for this this problem, that we're focusing on survival. Okay. So and again, let me make this clear. Odds, at least for me, maybe I'm just simple-minded, but odds for me are easier to interpret when I get a value above 1. To me, odds are tougher to visualize, if you will, when you get something between 0 and 1. You can always force something bigger than 1 if you get something between 0 and 1 by taking the reciprocal. But keep in mind, instead of, in this case, survival, we'd be looking at non-survival. All right, boys and girls, we ultimately want to look at the odds of survival for a male to a female. So therefore, I could take the odds of a male survive to that of the female survive, which is going to be equal to 0.2220. And I think if I did everything correctly, let me just double check that. Pretty sure that's right. So the male surviving would be 142 over 709. And the female surviving would be 308 out of 154. So ultimately, guys, that's what we have right there. And let me just very quickly, I don't want to have any rounding error that comes back and haunts me later. So 0.1001. Okay, cool. All right. All right, now what I want to do is I want to examine the natural log of the odds of male survive over female survive. So ultimately, guys, what I have here is I have the natural log of 0.1001, which I don't know, is negative 2.30. Okay, now let's take this information and make some calculations, okay? The regression model the logistic regression model turns out to be this. I'm going to give you more on this in the next video, but is the log of the odds which is in this form. So guys, on the left hand side, instead of having something very nice and neat being y, which might have been, I think a previous example we've looked at was, you know, a first year GPA. The y, if you will, in this case, is actually the log of the odds, which is equal to beta 0 plus beta 1. Something that will be interesting to us if we take e to the log. And guys, in all cases, Chris Treen, I bet this is driving you absolutely crazy. Remember, once you get into big boy, big girl statistics, when I use the symbol log, I am indicating natural log. So if we exponentiate, we can see that e to the power log odds is e to beta 0 plus beta 1x. So we can see it over here. The odds will be just given as a beta 0 beta 1x. So we'll demonstrate that via this example. So guys, again, what are we trying to do here? We want to fit the model. The log of the odds by finding the estimates for these two values. Well, guys, it turns out, and you know, obviously, I think we've used interchangeably because I know that's what I'm probably going to just naturally using is B0 and B1. Well, guys, it turns out that B0 is really easy to find in this case, and B0 is just the log of the probability that x is 0 minus 1 minus the probability x is equal to 0. So guys, at the end of the day, what are we finding here? We're finding the log of the odds of a female surviving, because x is equal to 0. We're using gender, right? So gender x equal 1 was male, so x equals 0 would be female. So ultimately, we're finding here the log of the odds of a female surviving. So guys, we're going to have the log of, I'm going to go back to my chart. So the odds of female surviving were 308 out of to 154. So the log of 2. Bailey, you need help? All right. So we'll take the natural log of 2, and we get 0.693. Now, we'll calculate beta 1. Well, guys, it turns out that beta 0 plus beta 1x, as we talked about before, is equal to a log of the odds of a male surviving. So guys, we saw that this value right here was what, 0.693, right? Yeah. plus beta 1. And in this case, x is equal to 1. And we have the log. The odds of survival for a male were 142 to 709. Again, keeping in mind that we can, finding odds, we can either use the probability divided by 1 minus the probability, or we can do the count of a success, in this case survival divided by the count of non-survival. So boys and girls, at the end of the day, we have beta 1. It's going to be the natural log of 142 over 79. Minus 0.693. And we get negative 2.30. So guys, from the previous screen, we see that B0. Now, hadn't been that long ago. Do those numbers look familiar? Does the 0.693, has that shown up anywhere previously in anything that we've done? No, it hasn't. Has the negative 2.3 shown up anywhere before? I actually was going to do something. It actually has. So it was the natural log of the odds of survival for the male versus female. Okay. Well, it's gonna show up here in just a second. All right, gang. Our model. Is the log of the odds of a male survival is going to be equal to 0.693 times x. Now, here's where it gets fun. Interpretation. Now, we're creating constant models here. In other words, we have a B0. And we're really not that interested in B0, but we are always interested in our B1. So what would be the interpretation here? What we would say, is x increases 1 unit. So first of all, before we think of anything, what does it mean to increase 1 unit? Well, that's going from females to males. Because we coded, again, x is gender. So we're focusing on x here. So as x increases from 0 to 1 unit, i.e. going from females to males, we can say that the log of the odds of survival for males is negative 2.30 Okay, the log of the odds of survival for males is 2.30. Well, let's sit there. Let's do that. Now, obviously lower because we had a negative, okay? So the log of the odds of survival for males is 2.3 lower than for females. What? The log of the odds. What the hell is the log of the odds? Can any of you really conceptualize that? Can you? The log of the odds of survival for males is 2.3. Now, if someone tells me that I'm going to increase ACT by 1 unit, okay, 28 to 29, 16 to 17, fine. If someone tells me that I'm going to go, in a standard multiple regression model, if I'm going to go from, say, Democrats are coded 0, Republicans are coded 1, then if we have some conservative scale for females, it's so many units higher than for Democrats. I'm sorry, for Republicans higher than Democrats. But the log of the odds. Well, guys, I don't know. I've been doing this a long time. I started studying logistic regression, I think, in 1999. I have no earthly idea how to interpret the log of the odds. And so at the end of the day, the interpretation log of odds is too much for me. And you know what? It's too much for most people. In fact, I would argue that it's too much for anyone. So, guys, what we need to do is this whole log of odds thing is just too much. We need to convert this to odds, right? Now, odds are okay. The odds of getting a red ball versus a blue ball were, 5 to 10 or 0.5. The odds of getting a blue ball versus a red ball were 10 to 5. So that was twice as likely that the odds were double of getting a blue as a red. I mean, that's cool, right? Well, it turns out that all we have to do to get log odds to odds is exponentiate. So, guys, if I take e to the 0.693, what do I get? 2. If I take e to the negative 2.301, what do I get? Wow. I get 0.1001. Now, have we seen those values before? 2 and 0.1001. No, we sure have. And we saw those right there. And we saw it right there. So, guys, what we can do ultimately is we can now come up with something that makes sense. So, again, this is for our constant. And it's fine, Dandy, we've got it. But this right here is the coefficient that we're most interested in. So the interpretation here, what I would say is the predicted odds. A heck of a lot easier to interpret than the predicted log of odds. So the predicted odds of survival are 0.1001 as high. For males and females. The guys still, when I have odds that are less than 1, it's hard for me to really get a handle on this. So, you know, equivalently, instead of 0.10, we could take the inverse of that. And we could, you know, easily talk about the predicted odds of non-survival for males and females. Okay. Well, I hope we've accomplished a little bit here. Oh, I know we have. This is not as intuitively clear, I think, as simple linear regression and multiple regression. When I first saw this, I was expecting, you know, something different. Certainly wasn't going to be. I wasn't expecting that we were going to be predicting the log of the odds with our model. And again, I'll get into more theory in the next and final video. But anyway, guys, what I want to do now, I want to get out of this, and I want to show you how on, oh, Bailey's got a cool screensaver. That's actually where we stayed in Mexico. So, I mean, we didn't like stay there, but that was on the resort. So, guys, let's go to R. Now, before I do that, let me show you something. Yeah, I'm going overboard here, guys. I'll try to make this as quick as possible. I'm already at 51 minutes. What I've done here is I've got a data set Titanic, and it's in the CSV, so it's on my desktop, so I'm going to pull that up. So I've already gone ahead and created that. So, guys, as you should know by now, we need to set our working directory. And I want users, D. Darborough, desktop, and I want to go get my data, so I'll do that with read CSV. So let's look at our data, and you've got 1,313 cases. Again, the first thing we have, first column we have is gender. I think if I can ever get back up there. And the second is survival. Gender coded again 0 female, 1 male. Survival 0 not survive, and 1 is survive. Guys, hopefully by now you know we've got to attach this before we can do anything with it. Now, before I can possibly run any analysis, what I would have to do first is I'd have to change gender and well, I'd have to change my non-quantitative variables into a factor. So I'm going to go ahead and do that. So I'm just going to go ahead and make gender. So I'm going to make GEN as it stands a factor, and survive, I'm going to go ahead and, I forget, was it SUV? SUR, okay. And guys, I'll have this, the Excel file, I'll have it loaded on Blackboard. So I just like to always check things, make sure that we do have a factor. Yeah. And survive is a factor. And just to make it clear, if I look at gen, it's not a factor. So guys, I have to tell the program that tell R that you know, these represent not counts but really placeholders and factors. So, well, gang, it turns out it's really easy to do. What we do here was we're first of all going to I'll tell you what, let me show you how to do this first. If we do table gender plus survive, doesn't work. Perfect. I don't know what it is. we have to do. Well, let me try this. Maybe we have to use well, this is fun. Darn. Shoot. Let's see, I just did this earlier with something. I don't remember how I did it. Well, what I'm wanting to do is get names. Okay, wow. Okay, well anyway, I can create my table so easily by looking at gen, and I don't know why I tried to make that so difficult. But it gives us our counts that we saw before. So anyway, gang, we can run our model here. Now what we have to use here is we have to use what's called general linear model. So we start this with the GLM instead of LM. And obviously I want to predict survive from gender. But I have to tell the program that I'm going to run a binomial. Need a binomial probability distribution here. I'm not running a simple linear regression, and I tell the computer, tell R that by going family equal binomial. So gang, if I look at my model now, you can see that I have my coefficients of 0.6931, just as we calculated by hand. And you can see that the gender using 1 as the comparison, which would be males. So the coefficient would be negative 2.301. We can get a little bit more information here. We can go summary model. And I'm going to talk more about the deviance residuals in the next video. I intended to talk about it here, but it didn't work out that way because I'm restricted with time. And so anyway, we can get into the statistical significance of the coefficients. When we only have one coefficient, it's not, I'm sorry, when we have one predictor, it's not that exciting, but next video we'll get into multiple predictors here. So guys, at the end of the day, gender is a statistically significant predictor of success. And down here you'll see that the number of Fisher scoring iterations was 4. So as I said earlier, the maximum likelihood estimation process doesn't have closed form, and we use computers to kind of crunch through the iteration process. It took 4 iterations to come to the maximum value for the -2 log likelihood value. So something else worth showing you again, this negative 2.30 is the log of the odds. So if we want to get this back to just odds, we use EXP, and I can look at the coefficients for my model, and those values should look extremely familiar. And again, it's much easier to interpret. In fact, it's not even much easier, it's almost mandatory to do that to interpret. Something else that we look at from time to time is the confidence intervals. It gives it in terms of percentiles, but these are the bounds for the 95% confidence interval. So this is the confidence interval for the for the odds, and we have statistical significance here. If this confidence interval contains 0, then we do not have statistical significance. And up here, the p-value would have been greater than 0.05. And again, it goes back to the centering of odds, like we talked about earlier. Something else we can do. Well, I'll tell you what. I think I've done enough to you in this video, because we've now, I would say, we know just enough about logistic regression to be extremely dangerous. But I'll try to clear that up in the next video. So.